what you see on the screen are two current voltage characteristic curves. Now, right now, I'm actually doing the same, they're identical. They're being measured on different channels of the scope, but what this is the IV characteristics of a 6V6 vacuum tube. I'll show you a little more of what I'm doing a little bit later, but some time ago I did a couple of videos on using the analog discovery to do transistor curve tracing. And at that time I mentioned that at some point I would like to extend that to doing curve tracing of vacuum tubes. And the reason that I'm showing two on the same scope, and by the way, not all scopes can do two XY graphs, and don't worry if this doesn't make a lot of sense yet. What is happening here is I have the grid tied to the cathode. In other words, the grid to cathode voltage is 0 volts. The curve that I'm actually displaying is this curve. Let me turn a little more light on that. And you see here is the 0 volt grid line. And so what you are seeing is this one curve. Now, I could apply a variety of grid voltages and get a family of curves and things like that, but I'm not going to get that complicated on this, though I will point out how someone who wants to extend this could do such a thing. But basically what I'm doing is I'm displaying the pentode characteristics of a 6V6. Now this particular one, actually you'll notice it says 6AQ5, but if you look up the 6V6 in a tube manual, it tells you to use the curves from the 6AQ5. So first question is, how am I displaying this? What's the circuit look like, and what are the components that I need to do all of this? And then the second is, why would I do two of them? Well, one of the reasons is I have an oscilloscope, a DS4000 Rigol oscilloscope that has 4 channels. And one of the nice things about this particular scope is it allows you to hook up 2 channels and display them in an XY, and then another 2 channels. In this case, this is channel 1 and channel 2, and one of them is displaying the voltage and the other the current. And then the second channel is displaying the current and voltage on channel 3 and channel 4. Now right now these are in parallel. In a minute I will talk about why you need 2 displays. But basically the idea is to be able to compare 2 tubes for purposes of matching. Now if you recall a few weeks ago, or maybe months now, I did some videos on using a tube tester for tube matching, in which I looked at the question of whether you could use an emission type tester, or at least certain emission testers, to match tubes, and then compared that to the results you would get on mutual conductance testers. If you are interested in that and haven't seen those videos, you might want to go back and look at some of those. But those were done just using a meter. Here we're actually displaying a dynamic characteristic. So let me now show you the circuit and the equipment that I'm using to do all of this. The particular 6V6 that I'm working with is that one. I'm using the tube tester only to supply filament current, that is, to heat up the filament of the 6V6. the operating voltages are actually being supplied by another piece of equipment. This is a night signal tracer. And the reason I picked that isn't because of any characteristics of the signal tracer, but it just happens to have a 6V6 output stage, so I borrowed the tube, and it has the power transformer necessary to operate that tube, and it includes 2 windings that we can use in a circuit that I'll show you in a minute. So the basic idea of what we're trying to do here is I was trying to see whether it was feasible to do XY displays of the characteristics of 2 vacuum tubes at the same time so that you can match them. I think I have proven, at least to myself, that I can do that. So let me talk a little more about the circuit, and then perhaps we'll actually set up a second 6V6 and compare the two using this setup. So here is the circuit that I'm actually using, and don't worry, we'll simplify this in a second. The idea was to be able to display the current voltage characteristics, that is the so-called plate characteristics of 2 tubes at the same time on the same oscilloscope. And the way I chose to do that is by inserting a small resistor in series with the plate current. And you measure the voltage across that resistor, that represents the plate current. In other words, oscilloscopes don't measure current, they only measure voltage. So if you hook this to the ground of the oscilloscope and a probe over here to this point, you get a representation of the current. And you see that's coming up here and also going down here to this one. In a minute I'll explain why you can use the same point for both tubes. And then the screen grid is connected here. The control grid is connected to the cathode, and then the cathode provides the other channel. If you notice, the voltage between the plate and the cathode is the voltage from ground to this channel. Let me show you a simplified diagram of that. It might make it a little clearer what we're doing. If you just look at a simple diode and you apply an AC voltage across a diode, as you know, current will only flow when the top is more positive than the bottom. So when this is positive, current will flow through this tube, through this resistor, and through the transformer and back to the cathode. If you measure the voltage across this resistor, that is a representation of the plate current. And if you measure the voltage across the cathode to plate, that's a representation of the plate voltage. So we now have what we need, plate voltage and plate current. If you remember the curve that we were trying to display, along the x-axis is plate voltage, and along the y-axis is plate current. And if you remember, we are using 0 grid voltage. Now, we could have put any grid voltage on this we want. I chose 0 just because it's sort of in the middle. And you could certainly put together a circuit that would either allow you to select the grid voltage, perhaps with a switch, or maybe even step the grid voltage using some kind of a step circuit. I show one of those in the Analog Discovery Curve Tracer video, but it's only a 5-volt stepper, so it's not really appropriate for vacuum tubes. You'd have to either amplify that signal or provide a different circuit. So that is the basic idea of what we're trying to accomplish here. So how did I go about doing that? Well, the first thing that I decided is I needed a center tap transformer. And I needed a center tap transformer that could provide the 250 to 300 volts that a good output tube needs to operate correctly, because you don't want to be operating these tubes down in the 80 to 100 volt range, which is where, for example, most tube testers operate them. You want to be operating close to the actual conditions you're going to find in an amplifier. So why did I need a center tap transformer? Well, the reason is so that when this cathode is negative relative to this plate, this tube is conducting. But when this is negative relative to this is positive relative to this, and this tube is cut off. So for a half a cycle, this tube conducts, and the current through this resistor is the plate current of that tube. The second half cycle, when this becomes negative relative to this, then this tube conducts and this tube turns off, and the current through that resistor is the plate current in that tube. So I'm actually taking advantage of the characteristics of a vacuum tube, that it is in itself a rectifier, as well as tying the control grid to cathode so that I get 0 volts grid to cathode. I'm also tying the screen grid to this point, and the reason I'm doing that is so that the screen grid always remains at or above the plate voltage. So even when this tube is drawing very little current, and therefore there's very little voltage across this resistor, the screen voltage remains relatively constant. So in essence, we are sweeping, if you want to think of it that way, the screen grid and the plate at a 60 cycle rate, while holding the grid tied to the cathode. And then we're displaying the current, that is the voltage across this resistor, and the plate voltage, that is the voltage between this point and this point. We're doing that on channel 3 and channel 4, and for the other tube on channel 1 and channel 2. Now, I'm going to talk a little bit about how I went about constructing this rather kludgy but nonetheless useful setup in order to accomplish what I'm doing. I started out with a tube tester that you may be familiar with if you've watched some of my other videos. This is a very simple Lafayette emission tube tester. Now for this purpose, all I'm using it for is to hold the tube in an octal socket with a tube extender that allows me to connect to all the pins, and then I am switching the filament across the filament transformer of this tube tester, but I'm not using the meter or anything else. In fact, except for the filament pins of this tube, there are no connections. I have all the rest of these switches set to the N or neutral position. So this tube essentially is floating with regard to anything outside. And so then the next question is, where do you get the voltages that you require to that center tap transformer? Well, I got that off a Knight signal tracer. And let me show you the schematic of that. Here's the schematic of the signal tracer that I used. And primarily all I'm using it for is for the purpose of taking advantage of this center tap transformer that will provide 575 volts AC center tapped. In other words, about 280 volts from each side of this transformer, which, by the way, is the rating for the 6V6, and that I'm using the 6V6 tube out of this. I admit that while this may seem a little bit kludgy, it is an example, I think, to young engineers that you don't need to go down the high-cost route when you're trying out a concept like this. Now, I know a lot of people right out of school, their first they would say, what's a vacuum tube? But assuming that they learn a little about vacuum tubes and understand that, their next question is, oh yeah, I know how to put together a system that will do this. We'll use MOSFETs to switch all of this stuff. We'll use zero crossing detectors to synchronize. We'll have a ramp generator that generates a nice linear ramp at 275 volts, and then we will switch it from one tube to the other tube using these MOSFETs and so on, and you've already spent a couple $1,000s. Well, I did this for $0 because I took advantage of the fact that I knew in this old signal tracer and in a lot of the old tube equipment, you can find a center tap transformer. Now, you can go out and buy one, but why buy one if you just want to test it? Also, if you wanted to, you could also use the filament voltage from this same transformer to drive the filament of the tube that you're testing. I chose not to do that, partly to reduce the load on this transformer so that I could use the maximum rating of this transformer, and also because I wanted to do some other testing, and for that purpose I wanted the tube to be out where I could get to it. But I could have simply just used this system and rewired the tube so that it operates in accordance with one of these half of this circuit. But I still would have been stuck with the situation of how do I get the second tube? And the answer that I have for that is I'm going to use a second tube tester. So what I'm going to do is have one tube tester hooked up on one tube and another on the other, solely for the purpose of driving the heaters of the two tubes. Now you might ask, okay, well, that's all well and good, but what about isolation? Because one of the problems that you will notice here is that I'm hooking an AC signal to the ground of the oscilloscope. Now, yeah, it's separated by a resistor, but this is only 10 ohms. For that purpose, you need to make sure that this entire circuit is isolated from the AC line. The reason is that modern oscilloscopes, the ground of the oscilloscope, which is one side of each channel, is connected to the ground of the power connector. In other words, it goes back to the ground in your service box, and from there it goes to the neutral. And so if you hook anything to the ground of the oscilloscope other than a floating signal, you can short out your AC power. And one of three things will happen. Either you will blow up your oscilloscope, or you will kick the circuit breaker, or worse. And by worse, I mean you can have a fire, you can be electrocuted, a lot of bad things. And that brings up a point that I do want to make. When working on equipment, any kind of equipment that is run off of the AC line, First, you want to make sure you're always using an isolation transformer. In this case, I'm using this isolation transformer to isolate the AC signals that are supplied to the tube. And just as a precaution, I'm using that isolation transformer to operate the tube tester, because I know that this tube tester does not itself have an isolation transformer inside. Further, I'm using a variable transformer over here so that I can change the voltage that I'm applying. And that variable transformer is connected to the AC input of this transformer that you see in the back here, which comes from the, or is a part of this signal tracer. So that's how I have set all of this up. One reason that I'm not going to be publishing schematics or any kind of directions on this is, frankly, working with these voltages can be dangerous even if you use isolation transformers, and I discourage, in fact, I hope no one who isn't an experienced technician who understands the safety rules of dealing with these voltages will even try to do what I'm doing here. Perhaps someone might want to put together an instrument that includes a power transformer with isolation and all of the other necessary parts here to supply. But if you are not an experienced electronics technician or engineer, don't try this on your own. Okay, now that we've sort of talked about how this is designed and how I went about deciding the method to prove its concept, let's move on now and try to put together a circuit like this that actually compares two tubes. Right now I have one set of channels connected to a tube and the other set of channels connected to the same tube. Now let's separate them so we can actually compare the IV characteristics or the plate characteristics of two different vacuum tubes. I know it looks like a rat's nest, and it probably is, but I've now set up two 6v6s. One on the right is the one I had shown earlier. The one on the left is a new one, or not a new tube, but a new setup with a 6v6. This is a new old stock tube. The one that is over here, you may recall, is the one that came out of this signal tracer. So what I've done is duplicated the circuit, and just as a quick refresher, the circuit that I've duplicated is this one here, where I'm using two tubes and a center tap transformer so that one tube conducts and the other when the other is off, and so on. So I set it up expecting to get two different traces, but what I got isn't exactly what I expected. So let me show you that, and you can see if you understand what's going on. I figured it out after thinking about it for a while. Let me turn off some of this light, hopefully improve the contrast. And what you see isn't exactly what I expected. I thought what I would see is the same trace, that is the this starting from 0 and going up to here and then tracing up, but instead it has two traces. Now let me note a couple of things. Notice that this trace is slightly longer than this trace. Notice the gap here. Similarly, notice this trace is slightly longer than that trace. Notice the gap up there. So can you guess what's going on? Well, let me explain what I figured out after seeing this, and I should have anticipated it, but it's one of those things that, you know, when you do videos like this in real time and you set things up, you can sometimes get a surprise. But it's actually a pleasant surprise, and I'll tell you in a second why I say that. What's actually happening here is, this is the characteristic of one tube, and this is the characteristic of that same tube. And I'll explain why they're showing twice. This is the characteristic of the second tube, and this is also the characteristic of the second tube. Earlier, when I was just using one tube, when that one tube was turned off, there was no current through the circuit, so there was nothing to sweep the XY trace, and so you were getting just a line that vacillated between here and here. But now that we are sweeping both in the positive and negative direction, that negative sweep is an active sweep, because remember, it's the positive sweep of the other tube. So in other words, the negative sweep of this tube is the positive sweep of this tube. And so what we're actually seeing is the same trace twice. This trace is this trace, and this trace is that one. Now, what it shows you is that it actually gives you a double indication of the difference between these two tubes. These tubes are not matched. And notice this gap. Now, it would be nice if we could lay one of these on top of the other. This scope won't let us do that. But it does at least let us display two of them at the same time. And so what you can tell from this is these two tubes are not matched. But it also gave me an idea that I might be able to change this circuit up a little bit in order to get the positive of one tube and the positive of the other tube on just one display instead of requiring a scope that has two. Now, I'm going to think about that, and you might want to think about it too, and if you have some thoughts, put them in the comments. But basically what I was pleasantly surprised to see is, once I figured out what was going on, that this method actually does work. It allows us to match a pair of tubes. In this case, we see they're not matched, but if they were, and I'm not sure which one is which, I'd have to trace it out a little bit, but one of these tubes is a little better than the other tube. It produces more transconductance. And of course, in a beam power tube, it's not so much transconductance that's the issue, it's the total power gain. So this tells us that if you put these two tubes in a push-pull output stage, you would not have a matched pair. So I hope this gives you an idea of the usefulness of this technique of sweeping the voltage and current characteristics. But I also hope that you'll keep in mind that the kind of kludgy setup that I have here is really just a proof of concept. It's just to make sure that this whole idea works, not necessarily to produce a production environment. So, as usual with these, I hope that you enjoy them. I don't know whether I'm going to carry this experiment further or not, but for the time being, I think I'm going to call this experiment completed, though I will be thinking about it for the next few days and perhaps trying a few more things that I may or may not put on video. But at any rate, I hope you've enjoyed it. And if you have any thoughts or comments, put them in the comments. Like I've said before, I always read the comments. I don't always respond to them unless there's something that someone either asks a question that might be of general interest or opens up a line of inquiry that might be useful to pursue in the future. So please comment. Let me know what you think. And perhaps we'll revisit this issue in the future. In the meantime, I hope you have a nice day.